Okay, so today I would like to talk about basic mathematical concepts from probability and information theory. Mhm. So suppose we have a process referred to as a random variable where there are a finite number of possible outcomes, xi, where I equals 1, 2, 3, up to n, to each trial of the system. If the system is observed for a large number of trials, then the frequency of occurrence of each outcome will be approximately fixed, and as the limit of the number of trials approaches infinity, we assume that this frequency divided by the number of trials approaches a value which we call the probability of a particular outcome, written P of xi. The sum of probabilities, by this definition, is unity. And suppose the continuum of outcomes can be mapped to R to the n and define a countable number of intervals for each dimension of equal length delta x. We can now adopt the process for a finite outcome set and extend it to the countable sets of outcome interval volumes, which will define a probability, capital Pi, for each interval volume in R to the n. We can associate now a probability density, small pi, with each interval by dividing capital Pi by each interval volume. And this is probability capital Pi for each interval volume in R to the n equals probability density, small pi, of delta x to the power of n. Like the finite case, we have the normalization condition, the sum of probability densities, small pi, of delta x to the power of n equals 1. We can now define a probability density, P of x, for any point that x belongs to R to the n by taking the limit delta x approaches 0. And then the normalization conditions, sum becomes an integral of probability density, P, of x1, x2 up to xn, dx1, dx2 up to the dxn, what is equal to 1. And the probabilities of intervals can be recovered using definite integrals of the relevant density function. An important functional defined on random variables concerns the associated uncertainty, and suppose firstly that the finite outcome case applies and that P of xi is close to the unity for a particular xi. Then we can say that the random variable has a very small uncertainty associated with it, since the outcome of the trials is almost always the same. Alternatively, if P of xi equals 1 over n, then the reverse situation applies, since any outcome is equally as likely. Information theory provides an important measure of this uncertainty through the Shannon entropy, and the Shannon entropy H is identical to minus sum of P of x, I, multiplied by a logarithm of P of xi from I equals 1 to I equals n. And it is easy check that the first case above has Shannon entropy H approximately equal to 0, while the second case maximizes the entropy with a value of h equals a logarithm of n. And for the first case, we have p of xi that is close to unity for a particular xi. Then the sum of probabilities multiplied by logarithms approximately equals product of probability and logarithm for a particular xi that is close to unity, and logarithm of a number that is approximately equal 1 approximately equals 0. So Shannon entropy also approximately equals 0. And in the second case, we have all outcomes that are equally as likely. So Shannon entropy H equals minus sum of p of xi multiplied by logarithm of p of xi from I equals 1 to n, and that is equal to minus n multiplied by 1 over n multiplied by logarithm of 1 over n, and that is logarithm of n. The entropy also has the property that if an outcome xi is split into a set of sub-outcomes yij that j equals 1, 2, 3 up to m, then the uncertainty increases. We have entropy nu that is equal to h alt plus p of xi multiplied by hi of y, where hi of y is identical to the minus sum of q of yij multiplied by logarithm of q of yij from j equals 1 to j equals m, where q of yij is identical to the p of yij over p of xi. So we have Shannon entropy h nu equals h alt minus p of xi times sum of p of yij over p of xi multiplied by logarithm of p of yij divided by p of xi. Another important functional is the relative entropy, which is a measure of the distance between probability distributions, and it is defined as relative entropy d from q to p, and it is identical to the sum of p of xi times logarithm of p of xi divided by q of xi. It is the inaccuracy induced in assuming that a given random variable has a distribution q when in reality the distribution is p. An important property of this functional is that it vanishes if and only if p and q are identical. And it is worth noting that in general, the relative entropy d from q to p is not equal to the relative entropy d from q to q. It is possible to generalize these functionals to the continuum outcome case by providing a little care with the limiting process. So let's consider firstly the entropy. The formula can be applied to the subinterval formalism used in the limiting definition of a density. We can write h equals minus sum of capital Pi logarithm Pi. That is minus sum of delta x to the power of n times small pi times logarithm of pi of delta x to the n. that is, we have a logarithm of product. So we have sum of logarithms. And then at the end, we obtain minus sum of delta x to the power of n times pi logarithm pi minus n logarithm delta x. In the limit delta x approaches 0, the first term of entropy approaches to the limit h is identical to the minus integral of p multiplied by logarithm of p d to the nx, and the first term is referred to as differential entropy, and the second term diverges to plus infinity. The limiting process is more straightforward for the relative entropy. Relative entropy D from Q to P equals the sum of capital Pi times logarithm of Pi over Qi. That is the sum of delta x to the n times Pi times logarithm of Pi to Q over Qi. And the limit of this entropy is the relative entropy d from Q to P, and it is identical to the integral of P times logarithm of P over Q d to the nx.
Yeah, maybe one more comment. Yes, the limit of this entropy is, so yes, and there is integral P log P over Q, right? So we can rewrite P log P minus P log Q, because log P over Q is log P minus log Q, right?
Yes, yes.
So in that sense, we will have like a subtraction. So there's a mixed term P log Q that is subtracted, right? Maybe that's quite essential feature. Yeah, so I guess we can exercise this more explicitly on very specific cases. Okay, please move on.
Okay, so now consider a closed system that consists of a large number of still macroscopic subsystems that are interacting with each other. A concrete example would be a gas where various macroscopic quantities, such as total energy, can be measured for small but still macroscopic regions of the total gas volume. And given a short enough time scale, the number of particles in each subsystem that are in interaction with other subsystems will be small relative to the total number of particles within any subsystem. Thus, the macroscopic properties of each subsystem will evolve independently, at least on the short time scale. The implication of this weak interaction of subsystems is that the probability densities of each of the subsystems will be statistically independent. So we have density Q12 equals density 1 times density 2, where density 1, 2 is the joint probability density for the composite system of subsystem 1 and subsystem 2. Rho 1 and rho 2 are the marginal distributions obtained by integrating out variables from the other system. So let's consider a macro variable f and let the value in the two subsystems for B F1 and F2, as a microscopic time proceeds within the short macroscopic time, both will fluctuate about their mean values, namely the mean of F1 and the mean of F2, where the means will be expectations with respect to the densities. And the statistical independence of subsystems means that the mean of product of F1 and F2 equals the product of means of F1 and F2.
Yes, excuse me, small remark. Let us come back to row 1, 2. So, of course, this is density of probability, but for two independent events, it's well known that if two events are independent, the probability of occurrence of both events is proportional to probability of first event times probability of the second event, right? So if we divide this, so instead of probabilities, we are having the density of probabilities, but that's quite obvious where it does come from, right?
Yeah,
that's quite intuitive. And also this statistical independence of subsystems also is quite intuitive, that actually only in the case of statistical independence, this mean value of product of two variable observables is equal to mean of first observable times mean of the second observable. Simply, this is like for two disconnected physical systems. That's what you can say, right?
yes. As I said earlier, it is given a short enough time scale that the number of particles in each subsystem that are in the interaction with other subsystems will be small relative to the total number of particles within any subsystem. So we can assume that there are closed subsystems because of the time scale.
Yes, that's a very excellent answer. Thank you.
Okay, so consider now a subsystem on the time scale mentioned a moment ago. Many different microscopic configurations could occur and would be consistent with the assumed density rho. So consider a large number of such microscopic configurations. Such a group is commonly referred to as a statistical ensemble, and the density of such points in phase space of the ensemble will follow the density rho, since they represent a sample of this density. Consider now the time evolution of such a cloud of phase space points, or more precisely of the density rho. It may be regarded as a fluid in which matter is conserved, since each point is conserved as time proceeds. The conservation of mass equation in a fluid in the 2n dimensional phase space reads the partial derivative of the density rho with respect to t plus dot product from gradient and density rho multiplied by vector x equals 0, where the vector x is the phase space coordinates, which in this case are the position and momenta of the n particles within the subsystem. Explicitly, we have the partial derivative of the density rho with respect to t plus the sum from I equals 1 to n from the partial derivative of density rho multiplied by qi with respect to qi plus the partial derivative of density rho multiplied by pi with respect to pi equals 0. 0. Now, the laws of mechanical particles follow very particular types of equations, namely those of Hamilton, which read Qi equals the partial derivative of the Hamiltonian h with respect to Pi, and Pi equals to partial derivative of the Hamiltonian h with respect to Qi. By substituting this equation, we get the partial derivative of the density rho with respect to t plus the sum from I equals 1 to n from the partial derivative of Qi with respect to Qi plus the partial derivative of Pi with respect to Pi equals the derivative of the density rho with respect to t, what equals 0. Then we have the partial derivative of the density rho with respect to t plus the sum from I equals 1 to n from the partial derivative of density rho with respect to Qi times partial derivative of Hamiltonian h with respect to Pi minus the partial derivative of density rho with respect to Pi times partial derivative of Hamiltonian h with respect to Qi equals 0. In Hamiltonian mechanics, the second term on the left-hand side is referred to as the Poisson bracket between the Hamiltonian and density rho. And we write that the derivative of the density rho with respect to t equals the partial derivative of the density rho with respect to t plus Poisson bracket with density rho and Hamiltonian h equals 0.
Yes, so this is actually very good point. So there's the most abstract formulation of classical theoretical mechanics is by this equation which you have just shown to us. So this is d rho over dt is partial d rho over dt plus Poisson bracket between a rho and h, which is Hamiltonian, and this is equal to 0. So this is equation of motion for observable that is rho. Rho can be any type of observable, so it can be momentum, it can be position, it can be a function that is made polynomial made of momentum and position, and so on, so on. Furthermore, such equations of motion does occur in quantum mechanics, but in the case of quantum mechanics, this Poisson bracket is replaced with this commutator between rho and h. So in such case, rho and h are fully operators. That's a transition from classical physics to quantum physics is about usage of operators. So in quantum mechanics, all observables are operators. So this is very deep equation. So there's also a lot of analogies between classical statistical physics and quantum mechanics, also expressed by this equation. Also, there are mathematical properties of Poissonian brackets that are very much similar to mathematical properties of commutator. So this is really great. This equation has a very deep depth. So please do thus remember and reconsider. So you need quite much time to contemplate on this equation, especially in reference to very specific cases. Okay, please move on.
Okay, so this equation is referred to often as the Liouville equation for a Hamiltonian dynamical system and holds for any system, whether in equilibrium or not. And according to Hamiltonian mechanics, the invariants of the dynamical system, which are the functions of the dynamical variables only, are characterized as those functions having a vanishing Poisson bracket with a Hamiltonian H. Furthermore, if we assume the system has steady statistics, which seems a reasonable definition of equilibrium in general, then the partial derivative of the density rho with respect to t equals 0. And so we conclude that for that case, the density rho regarded as a function of the 2n coordinates qi and pi must be an invariant of the system. This is also the case for any function of the density, in particular the logarithm of the density. And this particular function has another important property due to the statistical independence of different subsystems. It is additive across the entire closed system, since the logarithm of rho 1, 2 equals logarithm of rho 1 times rho 2, and this is equal to logarithm rho 1 plus logarithm rho 2. The theory of classical mechanics of non-spinning particles tells us that there are only 7 independent such additive conserved quantities for a general mechanical system, namely energy and the 3 components of momentum and angular momentum. So we deduce, therefore, that the logarithm of the density must be a linear combination of these invariants. So suppose we characterize the macro state of a subsystem using the mean values of the invariants discussed earlier. There is an interesting relationship between this characterization and the Gibbs density from the last week. Consider the set of densities which have the desired set of mean values of the invariants, and further suppose that we have identified the appropriate set of coefficients for the Gibbs density that produce these mean values. What is the status of the Gibbs density rho among the large set of all possible densities Q with the given mean invariance? It turns out that it has the maximal entropy, and we can prove this using information theory. First, set the Gibbs density as follows. Rho equals E to the power of the sum of alpha I, where II are the time invariant quantities for the dynamical system, and the alpha I real numbers. We set I0 equals 1 and choose alpha 0 so that the density is properly normalized. The integral is unity. Consider now the following chain of equalities and inequalities. H of Q equals minus integral of Q times natural algorithm of Q, that equals minus integral of Q times natural algorithm of Q times rho over rho, that is equal to the minus relative entropy from rho to P minus integral of q times a natural logarithm of rho, that is less than or equal to minus integral of q times natural logarithm of rho, and it equals minus integral of q times the sum from I equals 0 to n of alpha I times time invariant II equals minus integral of rho times the sum from I equals 0 to n of alpha I times time invariant II, and that is equal to minus integral of rho times natural logarithm of rho equals h of rho. So we have used the non-negativity of relative entropy and the fact that the expectation values, means, of the invariants are the same for both Q and rho. This proof shows that the Gibbs density has the maximal entropy among all densities with the same mean invariance. And that's it.
So thank you for a very good presentation. Maybe first comment I will make. So all these probability distributions that are somehow used for predictions of for statistical description of the reality are using this concept of maximized entropy. So actually, you can derive various distributions for various type of particles known in physics, like for bosons, Bose-Einstein statistics. Well, two particles can occupy the same phase space, and also you can have a Fermi-Dirac distribution when the concept of occupancy of the same phase space is not possible. So you can derive various distributions using this concept of maximum entropy. However, in real life, when you have phase transition, what is a phase transition? So I would say a phase is a state, let's say, constant phase is like a phase when you have a political parties in society, and stability of support for given political party is somehow constant, maybe a small fluctuation, but it's constant. And for another party is also constant. But when there is a sudden political event, there's like phase transition. So this distribution starts to change. So this process of phase transition is not fully well described by statistics, by statistical physics. This is highly non-equilibrium process that has a very complex description. If this process is slow, then it starts to be easier, but in general, it's not. So basically, you are kind of referring to the cases of statistics that are kind of time independent from certain perspective. So when mean values of certain observables are fixed, that are your considerations. And somehow in such circumstances, the statistical physics and basically statistical description works well. So it doesn't work well in very non-equilibrium situation. And usually in a very non-equilibrium situation, you have to consider many microscopic degrees of freedom. And this makes things very complex in description, and sometimes it is unbelievably complex or even not possible to describe it this deeply and accurately. So yeah, so anyway, this you have used this very nice examples. Yeah, so guys, do you have any questions in regards to the presentation that was given? Yeah, so of course we need to digest these things deeper. All right, Dariusz Kotula, thank you very much for your presentation.